All right, so in this video, we're going to record a run through of Lab 9A, although some of this is good to do in class. And so this is kind of backup in case you needed another run through, which is always good. Ideas of hypothesis testing are not intuitive by any means because they often involve double negatives. So let's get into it. So hypothesis testing is the way we do inference. It's the way we test whether a sample statistic corresponds with a population. So some kind of population parameter. So our null hypothesis always says there is no difference between what you observed and random chance. And so there's no difference between the observation of this data and something that's going on in our population. It's just random. The alternative hypothesis HA says there is a difference. There's some outcome. And so the way we proceed with hypothesis testing is we always want to take the skeptic's hunch that the null hypothesis is true. There's nothing going on here. And we gather a case for disproving the null hypothesis. So usually they stem around a null value. So if we wanted to guess whether people are guessing at a 4-point quiz, the null hypothesis would be what? If they are guessing, this would be randomly answering the question. And so the null would say there's no difference between what you see in this test and what would happen if people were randomly guessing. So it would be that people are guessing, and that the null value for this would be, well, what percentage of people would get the answer correct if they were guessing? And for that, if it's 1 out of 4 questions, we'd expect about 25% to get it right. So when we have a null value, the null hypothesis says there's no difference between what you see in random chance. If random chance is 1/4, the null hypothesis would say that the probability of what we're seeing is 1/4. And this concerns what we're seeing in the population. So here's an example of what we could do. Instead of having a 4-part question, there's a 2-part question. So this question pertains to experimental design. What's good intuition for experimental design? If I want to test the effect of a drug and I give it to 1,000 people, or I want to test it and I have 1,000 people at my disposal, the first scientist says, let's give it to all 1,000 people and see what happens. The second scientist says, let's give it to 500 people and then not to 500 people. For 500 people, they don't get the drug, and we see, is there a difference between the two groups? So if you have any kind of statistical intuition, or if you have been following in this class, we want to control. And so we're going to say B. B is the correct answer. And so here's an example of 670 people. 999 said A incorrectly. 571 said B. So let's construct our null and alternative hypothesis for this. We're going to test this. So the null H naught says people are guessing. And if people are guessing, we would expect about 50% to get it right. We would say P equals 50%. This would be the proportion, correct? 50-50 guessing. And here the alternative says people are not guessing. Maybe they'd be getting, hopefully if they're not guessing, P is greater than 0.5. These would be examples of our hypotheses. So the null value would be 50%. So let's test. Now we have this information. We're going to use the central limit theorem to study the distribution of what this sample would have come from. What is the sampling distribution? So first, do we have independence? And we're going to say, let's give it a turn. Let's see if it was given randomly. It does not say, but good experimental design would say it was random. So let's say yes if the survey was randomly administered, or I should say use random sampling. That's the proper way to say it. And then large enough success, failure. So the success and failure rate depends on what we assume. Is actually, I'm going to check this. Is the failure rate based off our sample, or is it based off our null value? That's an important question. So let's go look back at lab 8 and see what the conditions were for that. Something we always have to do in statistics is check our assumptions. So lab 8, what does our actual central limit theorem say? Oh, it's been so slow. Here we go. Central limit theorem here, we always have to go back to it. It says the sample size is sufficiently large so that we have 10 successes and 10 failures. Okay, so we're going to look at the sample. That answers my question. So we want to say, is there a large enough success failure rate? Well, successes would be people answering correctly. There were 571. Well, that's greater than 10. That's good. And failures, people who answered incorrectly were 99. That's still greater than 10. Okay, so we have the conditions to satisfy the central limit theorem. Always got to do it. And so now that we know the central limit theorem holds, what does it say? It says we're distributed normal with the distribution P. P is going to be, boom, where is it? Oh, I got to go back to the right lab. Okay, P is 0.5. What we assume to be true. We assume the null is true. And the SE is going to be square root of P times 1 minus P over N. That's also what the central limit theorem says. And if you run this code like it is, you might get an answer, but it'll be incorrect if you did not specify N. So I saw this a lot in grading the last lab. We got to use the correct N. So in this statistic, in this survey, there were 670 people. So that will give us the SE. If I run this, I don't actually see what the SE is. I have to put SE on the line by itself. And then this tells me that P hat is distributed normal, 0.5, 0.0193. Okay, so that's a distribution of the people answered correctly if we assume the null is true. So to conduct our 95% confidence interval, we're going to say P hat plus 1.96 times SE and P hat minus 1.96 times SE. And so what was P hat? P hat was, I think, maybe we didn't answer this already, the proportion of people correct. So 571 divided by N. So that will give me my confidence interval. And we can see, does this give evidence whether we should reject or favor an alternative? Well, let's see. This confidence interval says that we're 95% certain. We can say with 95% confidence, the true value of people answering correctly, I could say the true proportion of people answering correctly is between, looks like 81.4% and 89%. Okay, that's what this confidence interval tells us. 95% confidence, the true proportion of people is between these values. So now to answer this question, what are we going to do with our hypothesis? The first question is the null in this interval? If yes, then we fail to reject a null. See, double negative, it's confusing, but if we say no, well, then that's sufficient evidence to reject the null. Okay, so in this case, I'll let you determine what are we going to do? Is our null value 0.5 in there? And then you can answer that. Okay, so that's the first step. First step of answering all these questions is using a confidence interval. But there's another approach. So take a deep breath, get a drink, jump around, and we're going to talk about how to use a p-value, a probability to evaluate our null hypothesis. The p-value is the probability of observing our data or something more extreme given the null is true. So I even have a song for this that we're going to cover. So assuming the null is true, what is the standard error? Here we go. Assuming the null is true, we already found the standard error. I kind of was jumping ahead. I gave you that a little bit. So if we use this value for the null, boom, it's 0.5. Here's our standard error. Now we can use this to calculate the p-value. So if we assume that this is our distribution of p hat, I'm going to put that information here. We know p hat is distributed like this. What do we observe? P hat that we observed was this value right here. Okay, so I'm going to make a pretty sketchy drawing because I don't have my pen on me. But let's make it green, yeah. So this tells us, this little bit of information here tells us we have a distribution that's got mean 0.5. That's our null hypothesis. Says it's 0.5, which also tells us something about the standard error is 0.1019. And so if we observe this value 0.8522, the p-value is a chance of observing something more extreme than this. So we want to find an upper tail probability. Now we can find out our p-value using what we've done before. So p-value is going to be p-norm of that value. And central limit theorem tells us what the mean and standard deviation are. Mean, standard deviation, and sorry, I didn't mean to do that. Why are you getting smaller? There we go. So if that's the lower tail probability, that would be this right here. We don't want that. We want the upper tail. So what do? Gotta do 1 minus. So we always got to draw and see what kind of probability we're looking for. P-values are always going to be something more extreme, so we're going to go more away from the mean. So that tells us a p-value. And that p-value, if we see something like really, really small with scientific notation or a 0, that's a very good sign. That means this is the chance that we observe the data we have given the null is true. Very low chance. That means we have evidence to reject the null. That's what this tells us. P-values tell us whether we can reject the null or fail to reject the null. Okay. So here's a review of what we do to interpret our null values. And then using significance level, alpha 0.05, this means if our p-value is less than 0.05, we can reject the null. So since this value here, it says 0, it's very close to 0 as far as the computer can tell. This means we have evidence to reject the null. And what does this mean in context? In the context, we can go back to what our null hypothesis says. Our null hypothesis said people were guessing, so this has evidence to reject the null in favor of the alternate, which says people are not guessing. In other words, they have some kind of statistical intuition. Answering the question. Okay, very good. So that's a very good example of how we can set these up. So I don't think I'm going to do all the problems for you. but I will just give you a few tips. It's a long video already on setting up the hypotheses if you wanted to. But first, please try doing this on your own without the help of me. And if you get stuck, let's talk about what these are. So here we said 60% of respondents said Facebook was accurate. If you read this question, you say it's looking at how Facebook categorizes interests. 60% said Facebook was accurate. That's our sample. How many people were in this sample? Always want to know that. It says 850 people. You have to kind of hunt for it. But you see 850 respondents. Okay, so that's some more information I want to get from the problem. And now the question is Facebook accurate? Well, the null says there's no difference between what Facebook is doing and random chance. So I could say Facebook is random or not accurate. It's just guessing. And then the alternative would say, yeah, Facebook is accurate. It's not guessing randomly what your interests are. So here's how we would set up our initial setup for hypothesis testing. So you can check the requirements of the central limit theorem if it fits. And then we want to go ahead and find our 95% confidence interval. And then we use our confidence interval. You can test whether it fits the null hypothesis. Oh, and we should say the null hypothesis, what's our null value? What's the actual proportion? People saying Facebook is accurate. I think this would be a case where we'd say 50% of people, because there's two options, accurate, not accurate. So we want to test, does our confidence interval contain this value? And if it does, if it doesn't contain this value, we can reject our null. Okay, it's gone. So this should say problem 10 here. Then we recalculate the SE using the null value and proceed doing our statistical test to find the p-value. You should get the same response as the same result as D. And we can do that in class if you have questions. And then this should say question 12. Okay, question 12 says first time registration for visitors to a new website of 800 people, that's n equals 800, p hat 84 registered. So that would be the proportion of people who registered. That would be 84 divided by 800 registered. Okay, we can check our conditions for the central limit theorem, construct our 90% confidence interval for who registered. And then what we really want to know maybe is, does this change your registration rate? Previously, the rate was 8%. So sometimes previous experience or data gives us a null value to compare against. So the null here, if we want to say, does this new website design improve registration? The null would say, no, new website design doesn't. Does not impact registration. If it doesn't impact registration, the registration rate would be the same, p equals 0.08. But the alternate would say, yeah, new website design does increase registration. So then we would say p is greater than 0.08. So then you could find your confidence interval, interpret this, and find out what our p-values are. So there are also examples of these kinds of problems in the textbook. So do your best to answer these, and please then we'll come to class with questions. All right, good luck.